Welcome to this video on eigenvalues and eigenstates, exploring the mathematical language of physical certainty in quantum mechanics. We will start with the conceptual foundations of these important ideas. Eigenstates are known as the stay-the-same states. In quantum mechanics, physical action is performed by an operator and typically changes a state. An eigenstate is the exception. It keeps its shape or identity even after the action is performed. This leads us to the fundamental equation. Operator times state equals value times state. The operator represents the question or action, the state is the physical system, and the eigenvalue is the numerical result of the measurement. The eigenvalue A is the actual numerical answer you measure in the lab. A key point is that you can never measure a value that is not an eigenvalue. For physical quantities, eigenvalues must be real numbers, mathematically representing the stretching or shrinking of the state vector. Eigenstates represent a state of certainty. If a system is in an eigenstate of a property, you are 100% certain to get the corresponding eigenvalue when measured. In any other state, the result is probabilistic. Consider the guitar analogy. A guitar string can vibrate in many messy ways. The perfect harmonics are like the eigenstates, and the specific frequency or pitch of that harmonic is the eigenvalue. Operators act like sieves. Most wave functions are mixed states, a soup of many eigenstates. When you measure, the operator performs a selective action, forcing the system into one of its allowed eigenstates. The most famous eigenstates in physics are the Hamiltonian eigenstates, also known as stationary states. The equation shown relates the Hamiltonian operator, the eigenstate, and the energy eigenvalue. These states offer stability in time. If a particle is in an energy eigenstate, its probability density does not change over time. Only the phase, an invisible complex rotation, changes, keeping the physical properties perfectly still. The concept of discrete steps, or the ladder of reality, is often observed when boundary conditions allow only specific, separate eigenvalues. This is why atomic spectra show that atoms only emit specific colors of light, corresponding to gaps between energy eigenvalues. We now transition to part 2, the act of measurement, exploring the process of going from possible states to an actual result. Before measurement, a particle exists in a linear combination or a multi-state soup of many eigenstates. Each term in the equation represents an eigenstate weighted by a coefficient c. The Born rule dictates the probability of outcomes. The coefficients c are probability amplitudes, which are complex numbers. The probability of measuring a specific eigenvalue a is the square of its amplitude, or the magnitude of c squared. The moment of choice is instantaneous. Measurement forces the mixed state to collapse, leaving only one eigenstate. If you measure eigenvalue at 2, the state becomes its corresponding eigenstate immediately. A subsequent immediate measurement will yield the same result. Eigenstates act as a mathematical basis. Just as coordinate axes describe 3D space, the set of all eigenstates of an operator can describe any possible state of a quantum system. They are the building blocks of the quantum universe. In part 3, we will look at physical examples to see eigenstates in action. In the infinite square, well, the eigenstates are sine waves that fit between the walls, having nodes that increase with energy. The eigenvalues are energy levels that grow as quote squared, with a non-zero minimum energy called zero-point energy. For the spring potential, the energy eigenvalues are equally spaced steps. These eigenstates describe vibrational modes, which are relevant to how molecules vibrate and how light exists in a cavity. Angular momentum, specifically electron spin, demonstrates a binary reality. Spin eigenstates only have two possible eigenvalues, up or down. The Stern-Gerlach experiment proved that measurement forces an atom into one of these two discrete eigenstates. Some operators, like position and momentum, have a continuous spectrum with no gaps. A position eigenstate is an infinitely thin spike at one point, while a momentum eigenstate is a quote plane wave stretching across all space. Part 4 will cover the golden rules, focusing on Hermitian operators, which are essential for why physics works. An operator must be Hermitian to be a physical observable. This is crucial because only Hermitian operators are guaranteed to have real eigenvalues, ensuring that all physical measurements yield real-world numbers. This property leads to the independence of states. Eigenstates of a Hermitian operator with different eigenvalues are orthogonal, meaning that being in one physical state guarantees zero probability of being in the other. When two different physical configurations result in the exact same eigenvalue, this is called degeneracy. It means one eigenvalue corresponds to multiple distinct eigenstates. The role of symmetry often explains degeneracy. For instance, in a hydrogen atom, different orbital shapes can share the same energy. Degeneracy usually implies a hidden symmetry within the physical system. Part 5 goes beyond the basics to discuss commutation and conflict between physical properties. If two operators commute, they share a common set of eigenstates. This means you can know both properties simultaneously with 100% certainty. When operators do not commute, they are in conflict, embodying the Heisenberg uncertainty principle. Knowing the eigenstate of one property, like position, means the system is a quote of all possible states for the other property, such as momentum. Quantum mechanics can be viewed as a perspective shift, or simply a change of basis, allowing us to describe the system using different complete sets of eigenstates, such as the position basis or the energy basis. If a system is not in an eigenstate, we calculate the expectation value. This value is the weighted average of all possible eigenvalues, determined by the state's composition or mix. Finally, let's review the concepts and mathematics of eigenvalues and eigenstates. To recap the concepts, eigenstates are the pure states of a property. Eigenvalues are the only possible measurement outcomes. Measurement collapses a mixed state into a single eigenstate. Regarding the math, real measurement results come from Hermitian operators. Orthonormal sets of eigenstates form the basis for all quantum calculations. Linear combinations allow the full complexity of the quantum world to be expressed. The big picture is that eigenvalues and eigenstates are the bridge between abstract waves and the hard numbers measured in the laboratory. Quantum mechanics tells us what we can expect when we look. Thank you for watching this video. We hope you will join the discussion.